Welcome to the Guild, everyone. Today, we are stepping into some seriously high-stakes territory on the Cambridge 9709 AS and A-level map. We're taking on what a lot of candidates think of as a totally unforgiving dungeon, transforming logarithmic and exponential functions, specifically those tricky power forms like y equals k times x to the power of n, and exponential forms like y equals k times a to the power of x, straight into linear form. You know, for a lot of students, this specific sector of the syllabus just feels like a trap, where they constantly leak marks. But we're not going to play it like that. We are going to treat this like a strategic open-world exam quest. Together, we're going to build your conceptual stamina, decode the exact logic the Cambridge examiners are hunting for, and make absolutely sure you secure your maximum loot, which, in this case, means top-tier marks. Think of me as your guild master for this explainer. I'm here to equip you with the absolute best mathematical armor before you drop into that exam hall. So, let's get into it.
Here is our quest map for today's explainer. We'll quickly decode the math quest, master that linear form, recharge with some procedural tactics, evade those nasty examiner mark traps, and finally, lock down our maximum quest marks.
Section 1, Decoding the Math Quest. Let's break down the rules of the game.
To properly navigate this map, we need to look at the exact assessment objectives that Cambridge demands. To help us out, let's look at two hypothetical co-op players in our guild. First, we have Alex. Now, Alex is our heavy tank. Alex is carrying way too much inventory weight, memorizing absolutely every textbook definition, but kind of lacks analytical agility when things get dynamic. On the flip side, we have Sam. Sam is our speedrunner. Sam just wants to dash through the level, rush straight to the final answer, and skip all the mandatory puzzle requirements. Well, here's the thing. The Cambridge mathematics syllabus scales dynamically across 3 levels. Level 1 is basic recall. This is your fundamental inventory, like knowing your basic logarithm laws off the top of your head. Alex is fantastic at this. Level 2 is application, which means actually transferring that baseline knowledge to specific unfamiliar equations. And finally, the boss tier, level 3, is critical evaluation. This demands systematic analysis and evidence-based reasoning. If our speedrunner Sam just blasts past the intermediate steps to write down a final number, they completely miss the critical evaluation tier. You literally have to chain all 3 of these levels together if you want to clear the stage with an A star.
Now, the command words in any Cambridge past paper are literal instructions on how to beat the level. Think of them as ancient runes. Analyze, evaluate, explain, calculate, show that. Imagine our speedrunner, Sam, glancing at a high-tariff boss prompt that explicitly says, show that the relationship can be expressed in linear form. But Sam, rushing as always, misreads it as simply calculate the gradient. By just calculating the final number and writing it down, Sam completely ignores the command to show that. That specific rune requires you to demonstrate the step-by-step algebraic manipulation. Boom, trap activated. The mark potential drains instantly to almost 0. Analyzing means meticulously breaking down the mathematical components. Evaluating involves actively judging the validity of the data you're given. If you misread these command runes, guys, you are casting the exact wrong spell for the situation, and the examiner will afford you no mercy.
Section 2, Mastering the Linear Form. This is where we get into the actual mechanics of the transformation.
All right, out there on the exam paper, you are going to encounter 2 very common enemy types. The power function, which is y equals k times x to the power of n, and the exponential function, y equals k times a to the power of x. Now, trying to find the exact, precise values of those unknown constants just by staring at a curve on a graph, it's incredibly inaccurate. It's basically a guessing game. So our strategy is to transform these curves into perfectly straight lines. But before you do anything, you have to remember the method mark strategy. Your stamina meter relies entirely on this. Cambridge cares deeply about your journey, not just your destination. Marks are awarded for demonstrating your logical process and showing the intermediate steps. If you just jump straight from looking at the curve to magically writing down the final values of your constants, you are literally leaving about 80% of your marks sitting on the table. You have to lay down your mathematical tracks clearly for the examiner to follow.
So let's picture Alex and Sam sitting at the collaborative tactical table, trying to tackle a power function together. It's a complete mess at first. Alex is totally overloaded, getting bogged down in theory, literally writing out a massive paragraph explaining the core definitions of logarithms without actually doing the math. Meanwhile, Sam is arguing to just type the raw data straight into the calculator, run a linear regression, skip the written procedure entirely, and just spit out the constants. As the guildmaster, I have to step in here because both of them are currently failing the method mark strategy. The golden path, the exact path the mark scheme demands, is to show the examiner exactly how you bend the function. You write down the base equation, y equals k times x to the power of n. Then you explicitly write out the step where you take the logarithm of both sides. You show log y equals log of the bracketed term k times x to the power of n. Next, you prove you know the multiplication law by splitting it into log k plus log x to the power of n. And finally, you drop that exponent down using the power law, giving you log y equals n times log x plus log k. By taking a few seconds to visually align this brand new log equation right beneath the standard linear equation, y equals mx plus c, you instantly and undeniably prove to the examiner that your new y-axis represents log y, your linear gradient m is exactly equal to n, and your y-intercept c is equal to log k. Keep it tight, keep it concise, but absolutely always show those algebraic steps.
Section 3, Mana Recharge and Tactics. We've hit a tricky puzzle roadblock, so let's regroup.
Quest pause, let's freeze the screen for just a second. As you gather your focus before we execute our final critical strike paragraph, it is absolutely crucial to make sure your strategic baseline is fully optimized. Whether you're traversing IGCSE, O-levels, or you're deep in AS and A-level territory like we are today, equipping yourself with the right frameworks week after week is how you level up your baseline score into that coveted A-star. So take a quick second right now to subscribe to AC Exams at the handle below and make sure to enable all notifications so you never miss our weekly strategic map drops. All right, Mana recharged? Let's dive into the ultimate execution procedure.
Okay, here is the ultimate 5-step procedural framework for transforming these functions and graphing them out perfectly. Step 1, deconstruct the question. Look at what you're facing. Is it the power form or the exponential form? Step 2, extract the relevant data from the table they've provided. Step 3, select your analytical framework. This means deciding whether to use base 10 logarithms or natural logs. Here's a massive pro tip. If the equation given involves e, the natural logarithm, ln, is your absolute best weapon. Use it. Step 4, execute with clear notation. When you calculate your new transform table values, write them down to at least 3 significant figures. Don't round too early. Step 5, present with correct terminology. When you actually draw that graph, your axes must be clearly labeled with your new transform variables. You're plotting log y against x, or log y against log x, not just the old y and x. If you label them wrong, you lose the format mark.
Following this precise method guarantees a high-scoring combo. First, you identify the given info. Next, you systematically plot your transformed points and carefully draw your line of best fit. But here is the absolute critical part, where so many candidates drop the ball. You must check for reasonableness. Let's say you draw your line and you find your y-intercept is 2. Okay, we established earlier that the intercept equals log base 10 of k. So log k equals 2, which means k equals 10 to the power of 2. That makes k exactly 100. Now pause and evaluate. Does a starting value of 100 actually make sense in the real-world context of the experiment they described in the prompt? By structuring your response and your thought process this way, you aren't just doing abstract math. You are communicating mathematical reality. And that is exactly how you fulfill those higher-order assessment objectives. Section 4, Evading Examiner Mark Traps. Time to hand control over to you for a live diagnostic check. Let's run Challenge 1, the Visual Radar Sweep. Imagine I'm putting a highly complex source data graph on your screen right now. The y-axis is labeled natural log of y, and the x-axis is x. The points form a perfectly straight line, sloping steadily downwards. You have a 60-second timer. Can you extract the chord trend from this relationship? A super common trap here is to just give a basic description and say, well, as x increases, y decreases. But remember the mechanics of our transformation. A negative gradient on this specific linear plot means that the natural log of our constant a is a negative number. Mathematically, if the natural log of a is less than 0, that implies that a itself must be a fraction somewhere between 0 and 1. And if a is between 0 and 1 in an exponential function, that means the chord trend represents exponential decay. Seeing straight through that linear illusion on the graph to the exponential reality hidden beneath is exactly what separates top-tier candidates from the rest of the pack. For Challenge 2, let's spot the defective items. We're going to use the examiner's own data to isolate 3 fatal flaws identified directly in the principal examiner reports. Mistake number 1. Vague answers lacking specific detail. If you literally just write, I use logs to make it align, you are getting 0 marks for that explanation. Mistake number 2, forgetting to check format and presentation. This is huge. When calculating your gradient from your line of best fit, you absolutely must pick 2 points that mathematically sit perfectly on the line you actually drew. You cannot just blindly pick 2 raw data points from the original table if they don't sit on your line. Mistake number 3, answers not specific to the given context. Let me show you why this one is a massive, massive trap.
Here, we can perfectly see the generic answer trap in action. Let's say our speedrunner, Sam, writes this final conclusion. The gradient is 2, and the intercept is 0.5. So n is 2 and k is 3.16. Do you see the problem? Sam is treating the math like a totally sterile puzzle in a vacuum, with zero connection to the real-world scenario described in the question. Now look at the context-specific gold standard provided by Alex. Alex writes, the constant n, derived from the gradient, is 2, indicating that the kinetic energy dissipated is proportional to the square of the velocity. Do you see the difference? The gold standard explicitly takes those calculated numerical values and links them straight back to the physical reality of the question prompt.
Look, don't just take my word for it. This quote comes straight from the official Cambridge Principal Examiner reports as a definitive hazard warning. Quote, the classic mistake is providing generic answers not specific to the question context. Always link every point to the given scenario. In the high-stakes realm of 9709 mathematics, context is the ultimate key to victory. If X on your graph represents time and Y represents the mass of a radioactive isotope, then your final written answer absolutely must reflect that the gradient you calculated is tied directly to the rate of that radioactive decay. If you drop the context at the final hurdle, you drop the final marks. It's really that simple.
Section 5, Securing Maximum Quest Marks. Let's look at the final victory screen.
To make sure you replicate this successful full-mark quest compile in your actual exam, you just need to follow these 3 universal rules. Rule 1, the pre-quest question scan. Before you write anything, decode those command words. Decide immediately if you're dealing with a power function or an exponential function, so you know exactly which logarithmic transformation path to take. Rule 2, the stamina pacing matrix. Don't rush the algebraic transformation. Take the time to explicitly write out those log laws. Show the examiner your method. Rule 3, the post-quest review checklist. Check your formatting. Did you label your new axes correctly? Did you use actual points on your drawn line for the gradient calculation? And most importantly, did you link your final calculated constants back to the specific real-world context of the question? And there you have it. You now possess the exact step-by-step blueprint to transform those complex logarithmic and exponential functions into linear form, secure absolutely every method mark along the way, and evade the contextual traps that snare so many other candidates. You have officially leveled up your 9709 skill set. But as you carry these new skills forward, I want to leave you with this thought. If a simple logarithmic transformation can completely straighten out chaotic exponential curves on a piece of exam paper, what other hidden, complex patterns in the real world can be decoded just by changing the mathematical lens we look through? Keep analyzing, keep exploring your map. Make sure you subscribe to Ace the Exams at the handle below, smash that notification bell for our weekly Level Up Masterclasses, and drop a comment right now sharing exactly which Cambridge subject and level you are preparing to conquer next. I'll see you in the next explainer.